The next case we're going to consider is when we have a constant force, but variable distance. And so in these examples, we're going to be always assuming that we have just a uniform force. It's always going to be gravity. So we're going to be increasing our potential energy of the things that we're moving around by like raising them up. So our work is going to be opposing gravity, but our mass is going to be all spread out over some region. And so the distance that the different parts of our mass need to travel is going to vary throughout our region. So this is in contrast to like when we are thinking about moving a stone. Okay. Instead, what you want to be thinking about is an example like the following, where we're thinking about building a stack of pennies up. Okay. And so if we wanted to think of the work that's required to stack a bunch of pennies off of some pennies spread out on a table, each of these thin slices is going up to some different height, y. Okay. And what we have, if we want to figure out the total work required, what we're going to do is we're going to sum up the work to put each penny on the stack. Okay, and so for each penny, we can think of this as if it was a point mass. So our force here is going to be from gravity. So our force is mass times our gravity. So I'm going to think of this as mass times 10 meters per second that we're going to be exerting. Here I'm using positive 10 because gravity is pulling down on this penny and we are applying a force to pull it to fight gravity. Okay. And so so the work for one of these pennies, when I just write this Wi, is going to just be this force times maybe yi. How far up in the stack we need to go. Okay. Which we can write as the mass times gravity times this distance. Okay. All right. And then when we figured out the work to move an individual penny, we can add them all up and it'll tell us our total work. Okay. All right, we're going to use the same principle just in general. So we're going to think of slicing the parts that we need to move into slices that are at the same height. Okay, we're doing that because we want every we want to have a uniform distance within that height. So uniform distance to travel within that height. Within that slice, yeah. And then these are going to be thin little slices, kind of like a penny. We're going to multiply our force, which will be our mass times gravity by the distance that that particular slice needs to move. So we're going to find the distance we need to move that slice. Okay. Okay. And often we're going to be working with things like fluids. And so rather than being like a penny where we say this slice weighs 2 grams, often the information we'll have to work with is going to be density. Okay, so let me just talk you through the way that we can think about this. So we say our work is the sum of all of these little works that we're calculating. And so we write that with an integral as it's the integral of these little works, dw. And I'm going to write a little branching tree anytime I want to multiply two things together. And so the physical principle behind work is that work should be a force times our distance. Okay. And so our slice has some distance it needs to move. Okay. And that'll depend on like our problem and some force. Okay. And if we think about moving a penny, the force that we need to apply to move it is pretty small because pennies don't weigh very much. And so I'm going to write this as df. So the thing that's making work small is because we just have a little force that we need. Okay, now force is mass times acceleration. So I'm going to write this branching to say we're multiplying these things together. And so we said mass times acceleration. Acceleration due to gravity is 9.8 meters per second squared. We're often going to approximate this as 10 meters per second squared, except on the homework where it's always going to ask for 9.8. But like when we're doing problems in class, we'll just use 10. Okay. And so the force we're applying is going to be opposing gravity. And so we're using this 9.8 with a positive number. Okay, so we have mass times acceleration. This little force is little because our mass is little. And so I'm going to write this as dm, just a little mass. Okay. So if you think about the mass of your penny. Okay. And if we had individual masses like this, we could leave it here, but usually we're not going to have this kind of information. So we can think of mass as a density, which we write with a rho. And density is going to have units of mass per volume. Okay. Okay. Just gonna make this a little bit smaller. Move it out of the way a little bit. Okay. And so to get our mass, we take our density times our volume. Okay. And if we have a little mass, it'll have a small volume. So for example, the volume of a penny is pretty small. Okay. If we are thinking of having these really minuscule slices, our volumes are going to be quite small. Now, when we have something like a penny, one of these slices, there are a couple of dimensions that are small and a couple that are big. So a small dimension here is going to be the height, and I'm going to just write this dy. And a large dimension is this space. I'm going to write this AY, our cross-sectional area. Okay. And so our volume is going to be given by this area, cross-sectional area of our slice, times this little thickness dy. Okay. And so we're going to multiply all of these guys together, and it's going to give us our work. This is going to give us dw. We can integrate this, and it'll give us the work done. So let's try this out with an example.